Okay, so let's take a look at 2.2, number 13. Uh, Now, this proof will be a little different. It'll feel a little different from some of the other proofs we've done. So we've got G star as a finite group. Identity is E, and there's an even number of elements. Um, so we need to show that somewhere in the group G, there's some element that's not E, where if you square it or do A star A, you get the identity. Okay, so there are various solutions to this that you can find online, but I think that most of them are probably slightly out of reach right now. So here's one that I think is probably the best one for us. Okay, so first, I want to note something. First, note A star A equals E means the same thing as A equals A inverse. And here's why, right? So if we start with A star A equals E, and then I multiply, or I don't know, yeah, sure, let's say multiply both sides on the right or on the left, it doesn't really matter, by A inverse, then really it looks like this at first, I guess. And then we know it's a group, so it's associative. And A star, or A inverse star E is going to be A inverse. We know A inverse has to be in the group because that's one of our properties. We know that the inverse times A is the identity. And then the identity times anything in this set is just the original, is just the other element. And so we end up with A equals A inverse. Okay. So what this is really saying is show that there exists some element A that's not equal to the identity where A equals its inverse. Okay. So let's pair up each element of G, or in G, the set G, with its inverse. Okay. Okay, so let's say that we, well, actually, here, let's think about this. Let's say X gets paired up with X inverse. Now, the inverse of X inverse is going to be back to X. So if X goes with X inverse goes with X. So at most, any single element gets paired up with just one other guy, and the reverse would still be true. If you wanted to pair up its inverse with something, you get the original back. So they come in at most pairs, right? There's also going to be E, which is its own inverse. So let's see, how do we phrase this? Since X equals X inverse inverse, right? The inverse of the inverse is back to the original. Each element is paired with, at most, one other element. That's if X and X inverse are different. Otherwise, something like E comes along and it's paired with just itself. Right. We know E star E equals E, so E is its own inverse. And is paired with itself. Okay, so let's suppose only E is its own inverse in the set, in the group G star. So only E, right? Well, if no elements are paired with themselves, themselves other than E, then we'd only be able to account for, let's see, how do I want to write this? We'd only, I'll write it just like that, be able to account for an odd number of elements in G, right? Because if you're not getting paired with yourself, you're getting paired with something else. So that's 2 elements at a time. So each time you do that, you've got 2 elements, then 4 elements, and 6 elements, and then you've got E paired with itself. So 2 elements, 4 elements, 6 elements, you've got an even number of elements plus 1, right? So since G is even, we'd have a contradiction. So our assumption must be false. Assumption that E is the only element that is its own inverse. Must be false. Therefore, G must have at least one other element that is its own inverse. Okay, now if we extend this, I'll just put a little note here. Note, you could end up, get, or let's say end up with 3 or 5 or 7 or any other odd number of elements with the property that those elements are their own inverses. Inverse. Right, besides E. So, because if it had like 10 elements in the set, and you're pairing up the ones that aren't inverses with each other, you've got 2 or 4, let's say you had 4, right? Well, you still have E, so that's 1 more, which means the other 5 would have to be paired up with themselves, right? You'd be left with an odd number because the total has to be even. All right, so I hope that helps a little bit, yep, that's